Hi, I'm Zhenghao. This is Group 4. Today, my partner Zhenghao and I will summarize and share with you some of our findings and experiments on neuromusic synthesis. And this is our table of contents. Neuromusic synthesis, which doesn't have a clear definition, in our opinion, is applying AI technology like neural network in the field of music creation. With this technology, people who are not professional can also create music. Also, neuromusic synthesis can break the fixed pattern of music creation, generating some new or kind of music, which can bring new inspiration for musicians. So currently, neuromusic synthesis has been applied in many scenarios. For example, in the field of art, Huawei used neural network to continue Schubert's famous Unfinished Symphony No. 8. Google has also launched a Bach Doodle, which can harmonize the notes selected using the model training on the 306 Bach pieces to generate a small melody in Bach style. Another application is in the content creation. Apps like Ampers can automatically generate music for video, which can bring some new ideas to the creator and save creators' time. So before talk about the generative music, let's talk about the music itself. So there are two types of way to store music. One is a common waveform file like .wav and .mp3. And the other is called the musical instruments digital interface file, MIDI for short. This file stores the pitch, duration, and velocity of each note at each time point in time. And the biggest difference between these two formats is that the MIDI itself cannot be sound and needs other software or hardware to generate. And the waveform does not explicitly store every note played by the instrument, and it often stores a lot of additional information. So it's way higher dimension than MIDI. So obviously, for these two ways of storing music, there are two types of model for music generation. One is called the symbolic domain generation model which will output MIDIs, and the other is called audio domain generation model, and it output waveform audio directly. So now let's state our goal for this project. We want to implement an experiment with some neural music synthesis model, and we have three-step plan. First, we aim to implement one model with our own idea. Then we implement some models referring to others' work. And the last, we try to do some experiments on the current state-of-the-art model. Now, according to what we learned in the course, the generative model is suitable for this kind of task.
All right, let me give a brief review about what is the generative model and what does it do. Given a dataset X of examples from it, which we assume they are sampled independently from some underlying distribution, a generative model can learn to approximate this distribution. After that, such a model could be used to generate new samples that look as they could have been part of the original one. Generative models are sorted into two kinds, implicit and explicit. For explicit models, PixelCNN is one representative model for tractable density, and WikiWe is one representative model for approximate density, and we will implement them under this category. And for implicit models, GAN is obviously the dominator. We will implement MuseGAN. There are lots of work that are trying to generate music with neural networks. Some models are for the symbolic domain, and some are for the audio domain. They are utilizing many generative models like GAN, WE, and other autoregressive models. There is also a conference, and a lot of research are conducted every year.
So next part is implementation. First, let's talk about datasets. We're using two datasets to implement the data. We're using two datasets to implement the model. The first one is called the log MIDI dataset, which contains 170 multi-track music. But inside the dataset, instruments in each file are different. So it's a little bit hard to use. So people further process the log dataset to form the log piano roll dataset. The dataset has 21,000 music, and tracks inside them are merged into the common 5 instruments: drums, piano, guitar, basses, and strings. For the third model we tried, OpenAI claimed they used 600,000 chord song with lyrics and metadata for training, which we doesn't have access to.
Okay, let's start with PixelCNN. PixelCNN is a generative model that uses autoregressive connections to model images pixel by pixel. According to the experiments done in the associated papers and also the implementation by ourselves, it did a good job in generating images. So an idea came into our mind, because music can be transformed into music notation, which is just a kind of images. Can we make PixelCNN learn from these images? So first, We need this MIDI image for training. Here I use piano in this part. If we have information about how high each pitch is at a certain point in time, then we can actually play the piano. As these two features are stored in MIDI file, we can transform it into an image from MIDI, where up and down means higher and lower in pitch, right and left means forward and backward in time, and only white pixels means a note will be played at corresponding pitch at that time. Now we get the image. As I mentioned before, PixelCNN is a deep neural network that can capture the distribution of dependencies between pixels. It sequentially generates one pixel at a time in the image along two spatial dimensions. But how does PixelCNN do this? Actually, if we regard an image as a random variable composed of pixels, the picture can be expressed as a joint distribution of them. And the basic idea of PixelCNN is to decompose the joint distribution and express it as a product of the conditional distribution shown in the equation. When processing the information of the center pixel, the convolutional filter considers all the surrounding pixels to calculate the output feature map, not just the previous pixels, which validates the order prediction of the autoregressive model. The mask is then used to block the flow of information from pixels that have not yet been predicted. And this is the architecture we used to implement PixelCNN according to the paper. And for training of PixelCNN, parameters would be updated by maximizing the likelihood estimate of the training data. And for image generating, we'll do it pixel by pixel. At first, we generate an image by passing zeros to our model. It should not affect the first pixel because its value is modeled to be independent of all other pixels. Therefore, we perform the forward pass and obtain its distribution. Given the distribution, we first sample and then update the image with sampled pixel values. In the following steps, we repeat this process until all pixels values are generated. This is great because PixelCNN considers directional and spatial reasoning here, which is similar to the process of creating music by humans. Here are some comparisons between real and generated images. You can find that for real image, there are less notes at the bottom. That is because for piano, pitches played by human are usually from C2 to G5, but PixelCNN could generate the pitches from A0 to G9 at the same time, which is impossible for humans to play. After cherry picking, some generated results are quite interesting. We will show later.
So when we think of the image generation, GAN will come to our mind. So this figure on the right is a classic GAN model. Then we can let the generator generate some samples and let the discriminators determine the identity between the samples and the true MIDI. After the ratio between these two models, we can get the generated music. And this is the idea of the second model we tried. And the data used here are preprocessed MIDI file with timing and velocity permitted and no range limit to C1 to B7. But the MuseGAN model not only want to try only one track, they try to generate music with multiple tracks or multiple instruments at the same time. So how to do this? One way is to use multiple GAN model, one for each track, and let them generate independently. But this way has two problems. One is the sound between tracks may be harmonic if generated independently. And music progression is important because we want a coherent music, but this simple model doesn't model this. So the author for the MuseGAN gave two solutions for these two problems. The first one is adding an extra intra-track vector Z, act like a composer that coordinates the generation of track, and using one discriminator for all tracks. And the second solution is divide the generator into two parts. One is called temporal structure generator and a bar generator. Temporal generator maps a noise vector to a sequence of latent vector, which expect to carry some temporal information. And then this temporal information are used by the bar generator to generate MIDI sequentially. And here is the final model structure. You can see it contains the generator for each instrument and a composer like the extra module for coordinate the different tracks, and the generator for bars are done sequentially. And here is the output from the training model compared to the original training data. You can see they are similar in some point.
In the last two generative models, we all used data processed from MIDI files. After doing some research, we found that now some companies are using the waveform of music directly as training data. VQVE is widely applied now. It compresses the data into a low-dimensional space, trains an autoregressive neural network, and then decodes it back to the high-dimensional space. We experiment with a very representative model of this idea, Jukebox. It is a pre-trained neural net designed by OpenAI, which generates music in the audio domain based on WQAE. First, let me tell the difference between WQAE and WAE. They're almost the same, except WQAE got an extra codebook, which is an embedding table. WQAE wants to discretize Z by using this table. This process is also called vector quantization. In the codebook, we want to find the one that is closest to the vector embedding, such as Euclidean distance. Then use this embedding index to represent this vector. Jukebox actually uses 3 levels WQAE as shown below, which comprise the raw audio in 3 levels degrees respectively, with a codebook of the same size for each level. And each level independently encodes the input. The bottom level encoding produces the highest quality reconstruction, while the top level encoding retains only the essential musical information. Great. It could help successfully model important features that span many dimensions in data space, which does make sense to audio. About generating, we need to learn prior over the compressed space to generate samples, and Jukebox breaks up the prior as shown in the slides. Under this idea, a cascade of transformer will generate codes from top to bottom level, after which the bottom level decoder can finally convert them to raw audio. And here is an example of a waveform generated by Jukebox.
Here are the details of the 3 models we experienced with. You can see that these models are more complex than the other and require more computational resources. The relatively simple PixelCNN only requires CPU, but the remaining 2 require GPUs to run. PixelCNN trains took 2.5 hours, while MuseGAN trains took nearly 24 hours. Although OpenAI Jukebox does not provide information on training time, we believe that the training takes several days and require a multiple GPU setup. In the inference process of generating a music sample, we can also see that as the model becomes more complex, it takes more time to generate.
Now, let me show you the results. So first, this is the result from the PixelCNN model. You can find that it sounds good in some fragments, but not coherent overall. That may be because the size of the receptive field is limited, cannot cover the whole image when generating pixels. And this is the results from the MuseGAN model. You can tell from the sound that this model can generate a harmonic multi-track music, and the overall style of the music is relatively compact. There will be no sudden changes in the style, but there is no obvious theme too. Also, there is a problem because the probability of a note needs to be balanced when generating MIDI. There is a problem of broken notes. This is the result from the Jukebox model with settings. Jukebox not only brings us mature and clear melodies in music, it also generated the singing of humans, though you could tell there does exist some laws if you listen carefully. It is also an outstanding generation result. Besides, Jukebox can let users customize the generated music in some aspects like style, singer, and lyrics. Now let's do some discussion. For PixelCNN, it cannot learn the meaning of each pixel in the MIDI image. Only the conditional probability is given for pixels within the kernel, which means the generation of musical notes doesn't consider the global conditions. This is hard to generate music with musicality. So there are some possible improvements. One is to increase the size of the kernel to increase the receptive field and let the model do completions instead of generate from scratch. MuseGAN is a more complex model that can generate multi-tracks music. The inter-track vector introduced is rarely effective and contributes to the coherent music the model generates. But it has the problem of broken notes which need to be solved. Jukebox is by far the most sophisticated model for music synthesis. It not only models high-dimensional data of sound, also introduces conditions. For the conclusion, in this project, we have learned about the forms and methods of neuromusic synthesis, both for the symbolic domain and audio domain. And the audio domain is more complex since it has to model higher dimensional data. When generating music, the model needs to learn the global nodes relationship instead of the local. And to our knowledge, the future trends in this field is for symbolic domain models, we need to find ways to generate more complex music with adjustable conditions. And for the audio domain model, we need to study the wave models to generate more realistic music without losing fidelity. Thanks very much. This is our presentation.